So next, continuing on with our Inter-AS Option A example, we're going to go through the detailed verifications, where again we had two different VRFs. We have VRF B that's on router 2 and 10. We have VRF A that goes from 3 to 7, A that goes from XR1 to router 4, and then B that goes from XR1 to router 8. We had VPN v4 peerings that were going from 3 to 1 and 3 to 2. This is VPN v4 BGP. Router 1 was configured as a VPN v4 route reflector. And then we have two separate eBGP peerings that are in the VRFs that go between router 3 and XR3. And then we have a VPN version 4 iBGP peering that's going between XR1 and XR3. Now, as we looked from the end customer's point of view, router 8 had connectivity to router 10. Router 4 had connectivity to router 7. But if we look at from the actual packet flow point of view in the core, how is the packet going to be seen, or what you want to think about here is how is the packet going to be seen on a hop-by-hop basis, and if we needed to troubleshoot it, what specifically would we be looking for in terms of forwarding? That are we making the decision based on the IP packet? Are we making it on the VPN or the transport label? Are we making the decision based on the VPN label? Because there are three separate verifications we would need to go through depending on where we are and what type of problem that we are running into. Now, specifically what we should see happen is that when a packet enters from, let's say, router 4. So we go from router 4 to XR4 or XR1, and we need to think about what particular routing table does it need to do the lookup in, and what is the next hop going to be. If this is in table A, and we have a VPN peering over to XR3, it means that we need to do a VPN v4 lookup on the final destination that we're learning from XR3, so that's going to be where the VPN label came from, and then the transport label is going to be based on XR3's loopback. So if we look at the two of these specifically from XR1's point of view, and we look at the show MPLS forwarding table, we want to know, first off, what is the loopback address of 13. This is going to be the topmost label, which is the one that is the transport. Then we're looking at what is the final destination. So the final destination from router 4's perspective is going to be router 7. So we're going to say, look at BGP, look at the VPN v4 unicast routes, and look for can we say all distinguishers? Or we just say the prefix? Prefix is going to be 7777/32. And we may need to say, for the route distinguisher, 100, 100. And it says the best route is coming from 13. And our received label is where? Received label is 16,006. So what this means is that when we see the packet transporting over XR1, it's going to come in as native IP, and then it's going to get encapsulated with the top label that is 16,000, and the bottom label should be 16,006. Okay, so let's look at from our packet capture point of view, and let's say we're going to filter this just based on ICMP packets. Okay, so let's go to router 4, and we're going to do a ping, and we're just going to do this for one packet. So ping 7777, source is loopback 0, and repeat count is 1. Okay, so we should see first off the packet comes in from router 4. This is the native IP packet. So this is where it's regular IP in Ethernet. When it gets to the next hop, which is XR1, we should see it encapsulating it in two separate labels. So 16,000 is the topmost transport label. This is the one that's talking about XR3's loopback. Then the bottom VPN label, 16,006, this is talking about the final destination. So we should see next the packet is going to get label switched out to XR2. XR2 is going to see it with a two label stack. It's coming in 16,000, 16,003, and then the IP packet. it's going to say that the final destination from my point of view is the loopback of XR3. Since I'm directly connected to XR3, it is the penultimate hop, or the next to last hop. It's going to remove the topmost label and then forward the packet out towards XR3. So doing that PHP process is removing one label from the stack. We should see it then forward as 16,003 and the native IP packet. Okay, so we have packet 1 to our third packet. It should be a one label MPLS stack that is, or excuse me, it was 16,006, not 3. Okay, from XR3's point of view, when we then look at the show MPLS forwarding table, it says locally I need to figure out what happens when someone sends me traffic with 16,006. But this one is going to be in the VRF table. This is going to be in VRF-A. That if it comes in with 16,006, it means that it's going towards the final destination 7777. And notice that the outgoing label here is none. It is unlabeled. This is because the link that is between router 3 and XR3 is not running MPLS. This is the whole point of the inter-AS option A, is that we're keeping the MPLS configuration separate between their providers. So this now means that packet number 4 along the path is going to be just the IP packet. So IP packet source is 4444, destination 7777. The layer 2 source and destination, this is going to be XR3 as the source MAC address, and then router 3 as the destination. Now when router 3 gets this, it's going to come in unlabeled inside the VRF, but then we're going to need to point this towards an MPLS tunnel. So from 3's point of view, it is directly connected to 2, who is the exit out of the network. This means that we're not going to be using a transport label, because again, router 3 is the penultimate hop, or the next to last hop, in order to reach router 2. So from 3's point of view, we would just want to know what is the VPN version 4 label that router 2 allocated. This is the one that we're going to be using on that direct link between them. So from router 2, if we say show BGP, VPN v4 unicast for 7777, it should say, actually no, this is connected to router 3. So router 3, we're going that direction. This is going to go as native IP. If we were pinging this destination, we would go one more hop to 10.10.10.10, and we would need to know what is the VPN label for 10.10.10.10, which is number, let's see, it says the output label is none. Let's look at the, oh, this is from router 2's perspective. This is 19. Okay, so we would be using number 19 from router 2, or router 3 to router 2. So let's say we go to router 8, and let's say we do a trace route. We're going to trace from 8 to 10. We should see the packet come in here as IP, go across between XR1 and XR2 as a 2-label stack. So it's going to be MPLS, MPLS, and then IP. Between XR2 and XR3, it's going to be a 1-label stack. Between XR3 and router 3, it's going to be just native IP. Then it should be, again, a 1-label stack between router 2 and router 3, and then finally just the native IP packet as it goes out. So on router 8, let's do a trace to 10.10.10.10. Source is 8888. Okay, so let's look at this as correct. So first one comes in, native IP. Next one is a 2-label stack. It goes to XR2. Okay, that's that 12. One of the labels gets popped off. XR3 is making the forwarding decision based on the VPN label. On the inter-AS link, it's native IP. It then goes back in the VPN label, goes out to the final hop, which is router 2, and it removes the packet to go to the final destination. Now, the reason this is important to know from a troubleshooting point of view and also from the lab point of view is that think about how they could ask you a question related to the design. What if they were to say, configure inter-AS L3 VPN, or just in more general terms, configure a VPN to match this output? That you would then need to know what's the difference between the inter-AS options, and in which case am I using unlabeled traffic versus using labeled traffic. Now we'll see that other differences between options A, B, and C are going to be the specific hops that we use labels or not. Okay, in both option B and C, we're going to have labels being used on all of the middle hops. And in option C, the VPN label is going to stay the same on every single hop along the way. Okay, assuming that the next hop is not changing for the VPN v4 route, and that really depends on our particular configuration. So ultimately, in this example, there's really nothing different between what we had previously done. It's just that we're doing it in multiple places. That we're doing the PE to CE config from XR1's point of view to router 8. We're doing the PE to CE config from XR3's point of view to router 3. We're doing it from 3 to XR3, and then from router 2 down this way. Okay, the other consideration is when we're doing the inter-AS exchange between router 3 and XR3, if we're not using the same protocol that originally came from the customer side, so like OSPF to OSPF, EIGRP to EIGRP, the end result is that those extended community attributes get stripped, and we would lose the encoding of what type of route that we're advertising. So this also means that if we have multiple paths, if we have an intra-AS L3 VPN path and an inter-AS L3 VPN path, we would not be able to choose the inter-AS one regardless of what type of attributes that we set onto the IGP route. Because as we talked about like in OSPF before, we have to choose an intra-area route over an inter-area route over the external 1 and N1 over the external 2 and the N2s. Now, of course, there are other workarounds, like we could configure a GRE tunnel between the customer sites and then run IGP routing directly over there. It just really depends on what the scope is of the question. Do we care about not only reachability, but traffic engineering in terms of which way the traffic is going? Then we would need to take these other attributes into account in terms of the overall design. Okay, there's a question, what if the providers were to have redundant links, what would that look like? Just another link with the same setup? Exactly. So for inter-AS option A, for redundant paths, the only thing we would do is to create another link, let's say between router 1 and XR1, and then just do the inter-AS exchange directly between them. So again, we would have another 2 sub-interfaces. We have one for VRF-A, one for VRF-B. We would have another 2 BGP peerings, and then we would be doing the redistribution between them. But you do have to be careful in this type of design though, because now let's say that we have the route that comes in from IGP. Okay, the route comes in from EIGRP. And we then advertise it from XR1 to router 1 as BGP. We redistribute it from BGP into EIGRP. And we redistribute it, so that's actually going down. That would be going down to like the customer. Okay, let's say that way. But we also send it to VPN version 4 BGP. Okay, it goes across here, and we're sending the update into the VRF. There is a potential for a looping condition because we're removing those VPN v4 attributes that would normally be preventing the loops. So if the route was EIGRP external to begin with, we don't keep who was the originator ID when we redistribute into BGP, and then we could potentially cause a loop when we redistribute back in. So same as like we saw in our ISIS example before, we would have to go a little bit beyond this and do some type of filtering. Like maybe we're going to set a community attribute when we come in from regular IPv4 BGP, because the key is that this route, it is not a VPN v4 route. It's just a regular BGP route that happens to be inside of the VRF, and there's no loop prevention mechanism other than the AS path, but the AS path is going to get lost when we redistribute from BGP into IGP. So it is a lot of components that are needed for the setup, which means that if you're doing it from scratch, it is a time-consuming config. But now that we have the kind of skeleton of the network built, we're not going to have to do this again as we go into the option B and the option C exchanges. What we're mainly going to be changing is what is that relationship between router 3 and XR3 when we're doing, so who's going to peer VPN v4 versus who is peering IPv4 in the VRF versus in the global table.